Next, we're going to continue talking about inferences for the difference of two population means. But this time now, how the samples are taken is different from what we had previously when we had the samples taken independently from one another. Now we have what are called dependent samples. So how the sample was taken from population 1 is going to depend upon how the sample is taken from population number 2 and vice versa. In the end, this actually will be very beneficial to us to be working with dependent samples. And what I mean by that is that, let's say if we're doing a hypothesis test for the difference of two population means, we will be more likely to find that difference in a dependent sample situation than an independent sample situation. So let's next talk about, well, where would these dependent samples occur and what do they actually involve? So an example, let me get my red pen out here. An example that I have often had my students actually go out and perform the experiment itself is to determine, well, which grocery store has lower prices on average? Let's say if we wanted to compare Walmart to Hy-Vee. And the key to doing this kind of experiment is to sample the same items at each store. In other words, have, let's say, match the two items up or pair the two items. So for example, maybe let's say you go to Walmart and you get a box of Wheaties, and let's say maybe it's, I don't know, $4. And then you go to Hy-Vee and you get the exact same type of item, and again it's Wheaties, and it is, let's say, $3.95. So $4 at Walmart for Wheaties, $3.95 at Hy-Vee for Wheaties. So now how we've sampled this item, Wheaties in terms of an actual breakfast cereal, how we've come about and sampled this item is dependent of one another at the two different places. Perhaps, for example, a particular brand of milk, whatever that brand might be. You sample that same brand at Hy-Vee, you sample the same brand at Walmart. So now again, the samples are connected in a way, they're dependent. Another example where dependent sample comes about, dependent samples come about, is, let's say you have some kind of medicine you're taking, maybe it's allergy relief medicine. And you're interested, well, does an allergy relief medicine actually work? Does it provide relief on average to patients? And so a pharmaceutical company would be very interested in something like this. When they do a clinical trial, they would investigate this. And the way that they do it is that for, let's say, the same person, before they take the drug, and then maybe a couple of hours after they take the drug, they take some kind of measurements on that same person to determine if there is relief or not. And they do that with one person, they do this also with a second person, and so on, so that every single person is contributing essentially two responses from, let's say, a population, before the drug is administered and after the drug is administered. Another example is that, let's say we're interested in this with respect to advertising. Has overall sales at McDonald's stores improved on average with their new advertising campaign? So before the campaign started, we have some measurement of sales for a particular item. After the campaign has gone for maybe a month, you look at that for that same item at that same store, how have sales changed? What are the sales now? And lastly, which of two types of running shoes has the least wear after 1 month? You know, maybe you get a pair of Nike shoes and also a pair of some other pair of shoes. And let's say a person wears brand 1, let's say on the left foot, brand 2 on the right foot. And after, let's say, running for a month or a month period of time of wearing them and having periodic runs in them, you measure how the tread has degraded over time. Since the same person is being used for the two different types of shoes, the brand 1 population, the brand 2 population, you have paired essentially the observation of tread wear. And so thus you have a dependent samples that you're taking. Okay. So let's talk about the setup in terms of the notation. Let's let y11 be the value that we observe in terms of our sample from population 1, and for, let's say, item 1 in that sample. y21 is going to represent, sorry, I said that incorrectly. Let me restate that. Excuse me. y11 represents item 1 in your sample from population number 1. y21 corresponds to item 2 in your sample that came from population 1, down to, let's say, yn1, item n that was sampled from population number 1. Then let's let y12 be, let's say, item 1 that comes from population 2, all the way down to y sub n2, which would be item n that was sampled from population number 2. The key thing, though, is that y11 and y12 have something in common with respect to how this sample came about. y21 and y22 have something in common in terms of how the sample came about, and so on. So y11, y12 could be, let's say, Wheaties prices at Hy-Vee and Walmart. y21, y22 could be milk prices for a particular brand at Hy-Vee and Walmart as well, the same brand. So that's how our data, that's how we define our random variables. I could have done exactly the same definition with respect to the independent sample set of notes. In the end, it wasn't needed because of how we were going about investigating the statistics and the corresponding numerical quantities. Here, I do need to be that precise in my definitions. And the reason being is because of this. We're going to actually transform the form of our observed values to this form here. We're always going to take y sub I1 minus y sub I2 for the ith item in our samples that we're obtaining. And we're going to call that d sub I. So for example, with respect to the Walmart and Hy-Vee example, let's say that Walmart is population 1, Hy-Vee is population 2, and let's say y11 is would be the Wheaties price, $4. y12 is the price at Hy-Vee, and so that D1 is going to be 0.05 or 5 cents. And we're going to do that for every single set of observations that we have from our samples. So that now essentially you can say we have now one sample of differences. Now that we have one sample, we can essentially one sample, we can now basically go back in our set of course notes to what we did when we had one sample for one population mean and do all the inference procedures that we did then, now here. So, for example, we could find a sample mean and a sample variance, not for the y's, but now for the d's. Also, we're interested in the difference of two population means in order to make inferences to that. Now, since we're working with these differences, instead of writing it out like this, you could write it out now as, let's say, mu sub d. So the mean, population mean of the differences. And yes, we do have still two populations. But by using this notation here, that helps us differentiate it from what we were doing when we had independent samples. So overall, you can kind of think of this particular subsection of notes as being relatively easy, because now what we're going to do is apply all the stuff that we had for confidence intervals and hypothesis tests when we were dealing with one population mean. We're now going to apply it here to these Ds that we observe. Now, why is working with dependent samples better than working with independent samples? Here's why. One can actually mathematically show, and again, you would do this in a mathematical statistics course, that if we think of a random variable capital D for these differences, and D bar is this random variable version of that sample mean, the variance of D bar is always going to be less than or equal to than if we were to have considered these samples to be independent of one another, like we did in our previous set of notes. The variance of y bar 1 minus y bar 2. And the reason being is because since we have this thing that's in common amongst the things that we're sampling, we're basically removing that variability that you would normally have from our experiment. And that's why this variance will be more. To put it in an intuitive way, let's go back to this Walmart and Hy-Vee example. Imagine you go out and take a random sample of 10 items from Walmart. Imagine you go out and take a random sample of 10 items separately at Hy-Vee. Well, because most likely, since there's so many items in each store, most likely you're going to have different items in both samples. You're going to have a lot more variability to deal with respect to your prices than if you would sample the same item in Hy-Vee and Walmart and come up with 10 of these item pairs. Because now with those item pairs, when I'm comparing 4 to 3.95, you can see that these items are going to be essentially close to the same price. And so because of that, you're going to be reducing the amount of variability then that you're going to be dealing with. That's why working with a set of dependent samples, or sometimes people refer to this as paired data, is a much better way to do an experiment. And let's think about what having a smaller amount of variability then means in terms of inferences. So, what type of effect will this have on confidence intervals? Let's talk about then, what does our confidence interval usually look like? We take a statistic, that is, and we plus and minus a value from a distribution, a quantile from a distribution, like a t-distribution, times then the variance of that statistic. And so if my variance here of my statistic is now smaller than what it would have been before if I would have had independent samples, think about the effect that's going to have on the confidence interval. And we talked about this originally when we were dealing with just one population mean. If I have a smaller number here than what I had before, I'm taking that smaller number times this distributional quantity. So combined here, this is going to be overall a smaller number. And I'm adding and subtracting that always from our statistic. And thus now my confidence interval will be smaller in width, or in other words, narrower than what it would have been before if I had independent samples. If I have a narrow range for my confidence interval, hey, that's great, because that means I have a smaller set of numbers for where I would expect my parameter to be within. That's the effect. That's why this is so important. This could be a question then on a test. Now, later in the semester, we will continue with this idea of sampling items with some kind of connection, or this dependent sampling. We'll look at that later on, and this will actually be generalized to what we will refer to as a randomized complete block design. More on that later. Okay. So, well, what's a confidence interval now for this mu sub d, the population mean difference? It's exactly as what we had when we were dealing with one population mean before. The key difference is we replace the y's with the d's. So it's the same interval. So then, for a note here, please see previous discussions about its use then. For example, what happens to the need for the normal probability distribution when there's a large sample? Okay, so let's talk about an actual numerical example here. This example deals with some work that I've done with a pharmaceutical company in the past. And in particular, this pharmaceutical company was developing a new drug to treat schizophrenia patients. When I became involved with it, it was in what was called a phase 1 clinical trial. In case you don't know, there are typically 3 phases to clinical trials to determine if a new drug that's being developed is effective. Phase 1 is to determine, is the drug safe for people to consume? Can the body tolerate it? Phase 2 continues looking at that, but now it looks for a third item. Is the drug effective? Meaning it doesn't, let's say, cure someone of a disease or help them manage a disease. Then a phase 3 clinical trial then deals exactly with what phase 2 does, but now it uses much, much larger samples to make a definitive answer, to provide a definitive answer of, is the drug effective? Okay, so this was a phase 1 clinical trial. In fact, this was the second time that it was evaluated in a phase 1 clinical trial. So we were looking at how safe is it for people to consume. And it was evaluated at a number of different dosage levels. To make things simple for us, we're just going to consider the 3 milligram dosage level. And the drug was administered, and right before the drug was administered to people, at time 0, let's say, a test called the Continuous Performance Test, or CPT for short, was administered to a person. And then after that person was administered the drug, 4 hours after, this test, in case I didn't say this before, it's a psychometric test, was administered to the people as well. And this is what the test involved. The patient, or actually they would call them subjects in this case, a subject sits in front of a computer screen. And in front of the computer screen, you see a randomly generated number where the image is blurred a little bit. One number will appear every second for 480 seconds, and subjects will press a button whenever they see the number 0 appears. And what we were interested in measuring then with these subjects was what happens to the number of correct responses, meaning the number of times they pressed the button when a 0 appeared, which we called hits. What happens to the number of hits before the drug is administered and then 4 hours after the drug is administered? And the reason why this was of interest is that we were wondering, what are some of the side effects associated with this drug? Could it cause drowsiness? Could it cause blurred vision? Could it have some other detrimental effect then that would cause the person to change the number of hits that they would get? So you might, many pharmaceutical drugs have these kinds of effects where it might cause sleepiness. Well, if you're sleepy, you might not perform as well on this kind of a test. Now, alternatively, this drug possibly could be some kind of stimulant that I guess perhaps could help you be more alert and allow you to do better on the test. And so what we're going to do here is find a 99% confidence interval for mu d, which represents the difference between time 0 and time 4, on average, the number of hits in terms of generalizing to a larger population of people. So here's what the data looks like. This isn't the actual data. I'm not allowed to share that. So subject number 1, let's say at time 0 they got 47 right. And at time 4 they got 45 right. Do note that the number of zeros appears exactly the same for time 0 and time 4. So the difference then is 2. So they went down a little bit in terms of getting those zeros. Subject number 2, 34 times 0 times 4, 32. Again, a difference of 2. And there was a total of 10 different subjects in the sample. And so from that, we can find the sample mean, ends up being 2.8. So in fact, what you could do is simply add these up, divide by 10, and you get 2.8. You could also find the sample standard deviation. So what we could do is we take the d value, subtract off the mean of 2.8, we square it. So for person number 1, it would be 0.64. Do that for every single individual, add it up, get 15.6. So then the standard deviation ends up being 1.32. Okay. So now we have some data. What's the first thing that you should do whenever you get the data? Plot it. Take a look at it. See if it makes sense, the data that you observe. Maybe come up with some initial ideas of what you think might happen when you do inferences to the population. So since I have such a small data set, I just simply entered it in directly into tin, create an object called times 0 for times 0 values, time 4 for the time number 4 values, or time 4 hour values. Put it all in a data frame to print it out nicely. And let's look at some box plots and dot plots. So here's what our data looks like. We got a lot of these 2 values. But what's very interesting to notice is this. Here's my line at 0. So the difference of hits, if the hits go down over time, this value would be positive because I take time 0 minus time 4. And notice that all the values are above 0. So at least in this sample for these 10 subjects, it appears that perhaps this drug did cause some kind of detrimental effect because the number of hits, the number of correct responses was going down. So now you should think about that then in terms of if I want to make inferences to the population mean of these differences, what do you think the conclusion will be? Well, again, we have a small sample size here, but this is starting to make me think, uh-oh, there might be a problem here with this drug in terms of it is causing some issues here. We can also look at a histogram as well. There's our histogram. Obviously, we have a lot of 2s there. And so a question for you. So the corresponding code is for those plots is in my R program. Make sure you understand how those plots were constructed. So some questions. So why didn't I look at separate box and dot plots for each time period? Well, here's what it looks like if I would have done that. And based upon what we learned for independent samples, when we look at this box plot, we would say, hey, there is a lot of overlap between time 0 and time 4 hits. That overlap might make me think, okay, there's really not much difference at all between the population mean differences. Well, what we're seeing here then is the problem with this extra variability that one would have with independent samples. This would be an incorrect thing to look at. When we do take into account how the sample was taken and that this extra variability from person to person essentially is essentially the extra variability that would be there if you had different people is removed, so we have the same people, we can definitely see, hey, it looks like there could be something really going on here because this is all above 0. You wouldn't get that same conclusion if you would just looked at this particular plot. So what do you think about the normal probability distribution approximation? Remember, that would be essentially an assumption for working with the t-distribution in this case, and we do have a sample size less than 30. Well, obviously, we have some issues here with this normal probability distribution assumption. Again, as what we've seen in the past, or what I've described in the past, is that fortunately, these kinds of confidence intervals, the corresponding inferences, are what are often referred to as robust to non-normality. So even if we don't have a normal distribution, very often this kind of confidence interval still works out well. But even in this situation, I might be a little bit hesitant and actually perform a different statistical method too to see if the results match up. And in fact, I did do that, and the conclusions did not change, where this other statistical method did not rely on a normal probability distribution assumption. Now, one thing that I mentioned that unfortunately I skipped over here is that, well, how did I do this histogram with the normal probability distribution on it? Let's just review how I did that. So I used the hist function, and then I took time 0 out of CPT, my data frame, took time 4 out of CPT, subtract it, and then I used the usual code for the histogram, but one big difference is right here. For the freak argument, I say false. By default, it will be true, and what that means, it plots the frequencies for each of the classes corresponding to the histogram. If I do freak equal false, it makes an adjustment to the y-axis so that you can plot on the exact same y-axis probability distributions. If you remember, some people, when you're dealing with a continuous probability, when you're dealing with a probability distribution for a continuous random variable, people will often refer to these as probability densities. So notice the default y-axis value is density. I'm sorry, y-axis label is density. And so to then get the normal distribution on the plot, I use the curve function as we've done before, the d-norm function as we've done before, which corresponds to, is going to give me, let's say, f of x or f of y for a normal probability distribution. The mean that I'm using is simply, now I'm going to use the sample mean because this will give me an estimate of the population mean. And I do a similar thing with the standard deviation, color equal true. And a key part here, add equal true, meaning add it to the current plot. So that's how I did one of these plots. If that's unclear, please let me know, and I'd be happy to explain it further. Okay, let's go back to where we were. Let's see here. Okay, so let's actually find the confidence interval. Let me jump over here to 10. So I'm going to find the differences, find the mean difference, find the standard deviation of the differences, state my alpha level, find my sample size, get my quantile for my t distribution, and there we go. So again, d bar is 2.8. Now I just go to my regular code, or my code that we've seen before for our confidence interval for one population mean, d bar minus the quantile from the t distribution times the standard deviation divided by the square root of the sample size. That's going to be my lower limit. Upper limit exactly the same, but I put a plus there instead. And then I put everything in a nice little data frame to print it off. Let me hop back over to Word again. Here is my confidence interval. I also show here in the notes of how you can plug in the corresponding numerical values into the appropriate part of the equation for the confidence interval. Please note on a test, I might ask you to do that just to verify that indeed you can actually do it outside of R if you really had to. I mean, it's fairly simple in the end. And so here's my confidence interval. I am 99% confident that the mean difference in the number of hits is between 1.45 and 4.15. Another way to phrase the interpretation is that in 99% of similarly constructed confidence intervals, meaning you go out, take a sample, get a confidence interval, go out, take a sample, get another confidence interval, and so on. 99% of these similarly constructed confidence intervals will contain this population mean difference for the number of hits. So, some questions then. Is there sufficient evidence to indicate a difference in the mean number of hits? Yeah, there is. Notice I think the mean number of hits is between one, difference is always positive. And again, since I'm taking time 0 minus time 4 to find these differences, That means time 4 is lower than time 0. Something's happening here. One's, let's say, maybe alertness, one's ability, excuse me, to make these judgments is decreased for some reason from taking this drug. What would you expect the plots to look like if there was not a difference, or if there was not enough evidence to indicate a difference between the main hits? Well, I'll let you answer that on your own. Again, think back to when we were dealing with only one population mean, that section, what that kind of a plot would look like if there wasn't, if I was doing a hypothesis test of equals 0 versus not equal to 0 for the mean. Okay, here's a good reminder. Remember that the confidence level does not mean there's a 99% probability that this one interval contains mu sub d. Instead, it means that if many more samples were taken, we would expect on average about 99% of the confidence intervals to actually contain this mean. So here's a little bit easier way to perform these calculations in R. Use, as we've done before, the t.test function. So for the first argument, we have an argument called x. This is where you can put in essentially what you would refer to as population number 1. In this case would be times 0 values. Then y, that gives us our time 4 values, populate the sample from population number 2. My data is in a data frame called CPT. Confidence level of 0.99. And here's a very critical part. There is an argument in t.test that we have not seen before called paired. In this case, we want to call it true, or we want to use the true value with it, because now we have dependent samples. And again, some people refer to these as paired samples, so that's where this terminology comes from. The default value for paired is false. And so when we use the same function for when we were dealing with independent samples, that's why I didn't include that. So if I go ahead and run this code, here we go. Here's our confidence interval that we've had before. Okay. Now, what if we use the same function now, t.test, but now we only work with the differences instead? So, maybe perhaps we can imagine that this indeed was just a one sample problem. So I say x equal d, use what we did in the previous section for one sample problems, confidence level of 0.99, and guess what? I get exactly the same thing. I purposely did this here just to emphasize the fact that we're doing exactly the same thing as for the one population set of notes, but now we work with the D's instead. Well, what about hypothesis testing? Again, everything follows from what we've done before. So let's take a look at the confidence interval method to do this hypothesis test. We state our hypotheses. Mu d is equal to 0 versus mu d does not equal 0. We're looking for, is there any kind of change in these hits on average? We state our confidence interval, and what this means in terms of our original, what this means is that we reject HO because 0 is not in the interval. What does this mean now in terms of the original problem? Well, there is sufficient evidence to indicate a difference between the average hits at the two different time periods. Well, what about a test statistic? Well, when we came up with the hypothesis test for one population mean, we looked at a very similar quantity in the middle of two quantiles from a t-distribution, but it was written in terms of the y's. Here, now I write it in terms of the d's, so that now our test statistic then becomes d bar minus the hypothesized value of the difference of the means. And for us, it typically will always be 0. Very rarely would there ever be a case where you would want to look at something different from 0. Divide by the standard deviation, which is also divided by the square root of n. Okay, so how do we do then a p-value? Well, for a two-tailed test, take 2 times the probability of random variable t with n minus 1 degrees of freedom is greater than the absolute value of this test statistic. You can also do all this stuff in terms of one-tailed tests as well. I'll let you explore that on your own. There's, I think, a little bit later in the notes, we're going to look at it in a little bit, or in a little detail. But you should be able to do one-tailed tests based upon what we've done in the past. So, test statistic method now. State our hypotheses. State our test statistic is calculated to be 6.72. So again, here's D bar, here's S of D, and of course, here's the sample size. Something that's important to remember here when you have dependent samples. Note that the sample size is always going to be exactly the same for the 2 samples because since they're dependent in some way. I find my value, my critical value from a t distribution. Again, I would use QT to do this. It's a plus or minus 3.25. Then I graph it out in step 4. So we can see that our test statistic of 6.73 is way out there. It's very extreme with respect to this t distribution, meaning it would be very unusual to get the information that we did in our sample if the population mean was truly 0. So because of that, then, it must not be 0. So since 6.73 is greater than 3.25, we reject HO. Again, I expect to always see something like this on any kind of graded assignment, project, or test. So this means that there is sufficient evidence to indicate a difference between the average hits for the 2 different time periods. Thus, and this is key, the drug is having an effect on these patients. P-value method, well, I take that test statistic, I find the corresponding probability value, as you would expect, and this asterisk means times. This p-value is extremely small, meaning it's very unlikely to be that far out in the distribution if the null hypothesis was actually true. Well, let's take a look at then, what if we actually said these are actually independent samples instead? Would we reach the same conclusion? This is very, very important. So to do that, I use exactly the same code, but I changed, for emphasis, this paired to be equal to false. Here's my test statistic. Here's my p-value. Wow, look how large that p-value is. It's now 0.5 about. Before, we were getting something that was extremely small. Think about how this p-value then relates to these box and dot plots that we had. We saw a lot of overlap between the times 0 and time 4 values. This p-value makes sense relative to that plot. But what this shows you is there's this strong benefit of working with paired data, a paired sample, these dependent samples. Because if there truly is a difference between the 2 means, you're going to be able to find it much easier than if you were to treat it as independent samples. What about a one-tailed test? In this case, most likely, because of how pharmaceutical drugs tend to affect people, a research hypothesis could be that I hypothesize that one will be less alert on average after they take the drug. So I would look for mu d greater than or equal to 0. So to do this kind of a hypothesis test, I can use the t.test function again with alternative equal greater. And as you might expect, we get essentially the same conclusion. Okay. You can also see here's the corresponding one-sided confidence interval. Again, think back why I'm finding a lower limit for this particular problem rather than finding an upper limit. So that then concludes this section on working with dependent samples when you're doing inferences for the difference of 2 population means.